Okay, welcome back. Now, what we are going to do here is look at the soft potential functions the way we had looked at gravitational field earlier, and look at two particles and see how these particles are moving in a gravitational force field. Now, we can look at them how they would move in a Leonard-Jonesian 12-6 potential field, which we also call soft potential function. And as you understood from the previous section, that E r, which is a potential energy function, which is a property, which is a function of r distance. And as you know, in the time trajectory, the positions are also function of time. So, if you look at the time trajectories of all these different r vectors of each particle, and in case of Leonard-Jones, we look at the pair potential. So, we are now going to look at two particles and how they behave. So, if you look at from there, we can do computational programming and understand how the trajectories can be calculated using numerical methods, which is a big field by itself. We are going to delve into it specifically with the understanding of how to solve second order ordinary differential equation. So, with that understanding of acceleration on the forces, now the question comes about time step, and we looked at in our previous section that time step is very important parameter, primarily because the errors can be larger or smaller based on the time step. And also on one end you want to keep as big time step as you can, while at the same time you want to make sure that the error, especially because of the truncation of the Taylor's series to let us say the second order differential, we are able to have the error within the parameter that we wanted. And if you look at in the calculation of the time steps, the most expensive CPU calculation is what we call is the force calculation, and that requires calculation of through the big potential function which has bonded and as well as unbonded potentials. So, understanding that whole idea about bonded and unbonded, question comes is where is the CPU time going, and I explained to you in the times of supercomputers, that's an expensive that was an expensive proposition, but now it is not as much. But if you look at now, the number of particles have grown quite a bit. We now do million particles. That means still we need processors which have 32 processor unit, multi-core, all of that. We will get to that in the later sections, but let us focus on the two particle system now. So, in the two particle system, there are two forces. Now, look at your slide now. What we see here is that there are electrostatic forces, and then there are van der Waals forces, which are represented by unbonded potential. So, if you look at this unbonded potential, which has two terms, one is the van der Waals, which is represented by 12-6 potential, and the electrostatic potential, which is represented by Qi Qj over Rij. If you look at that, there is attractive forces between the charges. So, if there are positive and negative, they will attract each other. If they are positive and positive, if they come closer, they will repel each other. At the same time, due to the van der Waals forces, what the dispersive forces, we are able to see repulsive and attractive forces as well. Now, if you look at the right hand side of your slide, you can see this potential energy curve, which goes which is a very sharp curve with a potential well at the bottom, and then it becomes flat curve, and it goes long time, it becomes asymptotic with the zero energy, and so it is a very long range force for the attractive forces. So, if you combine the two, the repulsive forces and attractive forces, which is 1 over r to the minus 12, minus 1 to the r to the minus 6, that combination together gives you this potential function. So, now the question is how do we understand that. So, I am going to show you a VMDL simulation with only two particles, and most of the situation that we looked at, temperature, pressure, etc., we can also put it on this system and look at what happens to the dynamics of this two particle system. And they, if you as you will see their motion, you will see they are in a soft potential function. So, now let us look at the pair interaction in VMDL, and again this simulation in your tool is called 2 SMD2. So, now let us go and make sure you get a higher resolution. So, you have magnification here. Now, you can see particles clearly, and I am going to put some additional parameters. Let us look at what this simulation is doing. There are two particles, both are of the type green, and we can set some interaction between the green and blue and or blue and blue. So, because there are no blue particles or there are only green particles, we will look at the number density, we will look at the rigid container, or we can create a container with piston, as you can see up here, or you can, and this is a locked piston. So, there is again it cannot move, but I can relax the piston and put some external pressure on it. So, these are the parameters. We will start with rigid container. So, first thing we do, we start the simulation, and this is done under let us say argon atoms. So, now you can see these two atoms of argon, and they are going back and forth, and they are under, if you look at reflecting wall, and this is rigid container with a certain density of 0.1 and temperature of 0.029 reduced unit. So, if you multiply that by 12 as 0.1, it is very low temperature. So, now if you look at the temperature versus time curve, you can see as they come close together, the kinetic energy increases. So, let us look at the kinetic energy. You can see those two peaks. Let us look at the total energy, where you also have potential energy. So, as the particles come close together, they are feeling repulsion, they are repulsed back, the kinetic energy goes very high, and so at that point the potential energy is low, and you can see this behavior, and its temperature is also low. So, first thing what we are going to do is increase the temperature and see what happens to the system. Let us equilibrate it by running it for some time. Now, we have gone up to like 600 time steps. So, we are also talking about the time steps. So, we will keep track of that. Now, if we increase the temperature by let us say 2.0 reduced unit, we increase that. Now, you can see that they are moving in all directions because of the kinetic energy, and you can see on the right hand side, if you pay attention, that there also wherever there are some, either they are hitting the wall or they are hitting each other, you can see the potential energy curve go up and down, and so does the kinetic energy curve. So, let us look at that. I can pause that here, and then let us do an additional parameter here, which I will talk about in more detail, called no walls. So, let us see if there were no walls, what will happen to these system. Now, you can see that they are going out and coming back, they are moving all around. So, this is called periodic boundary condition, because what we have done, we have taken the central cell and then we have replicated infinite number of images around it. So, with that we are able to get periodic boundary condition. It is almost like if you take a small cell and you put inside, and there are a lot of images of this cell all around it, like in a bulk. And if I go microscopically and look at very small tiny section, but the material can go in and out. So, this becomes a almost like a imagination of a bulk system. There are no surfaces in this case, the particles can go back and forth. So, now let us put some pressure to this system and see what happens. So, I am going to create the container with the piston and start that. Now, you can see that it is pushing some pressure on the piston. Energy, you can see this energy versus time. Let us look at the pressure. Now, pressure also has some behavior that you can watch. And now, let us put some pressure to the piston. So, now I am going to have a piston that can move. Okay, so, I am going to change that. Now, you can see that the kinetic energy has increased quite a bit, primarily because we are also allowing pressure to increase, and density is still kept constant. So, you can see the pressure is essentially increasing the kinetic energy, and there is a breakage of the bond between them, if there was any bond. This is unbonded potential, but you are seeing that they are interacting much closer to each other, and if I really put some pressure on the piston lastly, then I increase the mass of the piston. So, you will see what happens to this system. Now, we exceeded the limit of the system with 2 particles. So, now you are seeing this situation with the piston with n number of such particles. So, let us do that with external pressure. Now, you go back to the familiar situation. Now, in this case, instead of 2 particles, we have 144 particles, and so what you can see with the pair potential, now you are taking the pairs of 144 particles, and then we are going particle by particle, looking at all different atoms together. So, now this becomes truly 3-dimensional system. So, we went from 2-dimensional system to now a truly 3-dimensional system. Thank you.